Hi, so what we're going to do in this video is talk about concavity and points of inflection, which are aspects of a function. We, in the past, have talked about a graph in terms of its rate of change, but what we can actually now do is, using its second derivative, talk about the rate of change of its gradient, or the rate of change of its rate of change. Another way of describing that is how quickly the gradient is changing, or whether the gradient is increasing, or whether the gradient is decreasing. So if we were to work out the double derivative, second derivative, and find out that at a point f double dashed x is greater than 0, we would describe that as concave up. At f double dashed x is less than 0, the graph is concave down. And at f double dashed x equals 0, there is a change in concavity, or a point of inflection. Important to know that we've called things at points of inflection before, which are true when they're rising or decreasing in their nature, and there's turning points or stationary points, but there is more than them. A point of inflection is generally just any point where there's a change in concavity, so it is not necessarily a stationary point. The reason they're called concave up and concave down, if you see I've tried to highlight it in a graph, what happens and where they look, you can see it's concave up because the curvature of the graph is allowing the graph to be, so if you were to be looking at it from that side, okay? It's a really bad way of explaining it. Concave up is because its gradient is increasing, and then concave down is because the gradient is decreasing. Another way we could describe it is if you draw a graph and you're not sure, if you try and draw the straight line tangent, if it's concave up, we're going to have to draw it below. Where if it's concave down, we're going to have to draw the straight line above. But the main thing to take from this is that concavity and points of inflection are another way of determining the nature of a stationary point. So I'll put a wee table up. If we know that f dashed x is 0, as in that must be a stationary point, and then we can find out what the double derivative is, we're able to state the nature. So if it's greater than 0, the double derivative, it's concave up, which suggests it's a minimum turning point. Whereas if it's concave down, then it is a maximum turning point. Whereas if it's 0, and 0 for the double derivative, we can't actually state its nature. We know it's a point of inflection, but we don't know whether or not it's rising or falling, so we would have to then consider the nature of the graph outside of that. That's a very specific case. So we'll do a standard higher question, but we'll be doing it a slightly different way. We've got concavity and points of inflection. Okay? Fixed my spelling, so you can't have a go at me. So I worked out the first derivative, and then I worked out the second derivative, and then I solved for the stationary points by solving for the derivative equal to 0 and then I substituted those x values into the second derivative. So for x equal to -3, we've ended up with positive 18 in the double derivative, which suggests a minimum turning point. However, we've got a problem of what happens at x equals 0. Well, it's turning out 0, so it's a point of inflection. So is that going to be a falling or rising point of inflection? So if in that case this happened, then you would just need to check the nature around it. So you would check x equal to 1 and x equal to -1. So there, all I did was quickly check that the gradient is either side of the point of inflection, and it's positive on either side. So it is a rising point of inflection. Okay, so that's how we can use concavity and points of inflection as an alternative way of stating the nature of a turning point.